All right, so this will be the tutorial video for section 13.3, day 2. We are going to take a look at something called curvature today. To kind of build that idea of curvature, let's look at some features of a graph that you would have learned about in pre-calc and in Calc 1, Calc 2 last year. So if you're watching this video, you're probably alone. You're not with a partner. So let's just do this solo. Here's a graph. Looks maybe cubic. Let's discuss as many features of that graph as we possibly can. So maybe pause me for a minute and see, based on what you already know from algebra, pre-calc, and calc, what are some different features of that graph that you would be able to identify? Think about extrema, concavity, increasing, decreasing behavior. Pause me, write down as many as you can, and then we'll check them. And then we'll move on to the second part. All right, so hopefully you had a chance to take a look at that. Here's the features I was able to identify from that graph. It has a local max at x equals -1. I don't know the full ordered pair because I don't know the y value of that function, but at least I know it has a local max at x equals -1. It has a local minimum at x equals +2. It's increasing on the intervals -∞ to -1 and 2 to infinity. It's decreasing on the interval -1 to 2. The concavity, I estimated where the point of inflection was at. So to me, it looked like it changed concavity at about x equals 1/2. So from -∞ to 1/2, it was concave down. And from 1/2 to infinity, it looks like that graph is concave up. So those are probably the features hopefully you were able to identify. So now the second question, this is kind of getting into what we're going to talk about today, is something called curvature. So in a more intuitive sense, if I was to ask you what areas of the graph seem more curvy, okay, I know that's a very loose expression, but if I was to say what areas of the graph look the most curvy, what would you say? Okay, can you narrow down any points in particular that tend to have the most curviness? And what areas of the graph seem to be less curvy? And what would you say, just intuitively, what makes you say that they're less curvy than those other areas? Okay, so maybe write down a couple thoughts based on that graph you have, and then we'll kind of look and compare with what I was thinking. And then we're going to obviously get into a more formal conversation about this idea of curvature. Okay, so I would say it looks like it's more curvy near those extrema, near the local maximum and near the local minimum. So I would say x equals -1 and x equals 2 tend to exhibit the most curviness. Notice I'm doing air quotes. Which areas are less curvy? Well, it looks like the end behavior tends to be fairly linear. I mean, I know it's not a straight line, but if I was to sketch in those tangent lines, most of those tangent lines would be moving in generally the same direction as x approaches +infinity, and likewise as x approaches -infinity. This curve tends to just continue to decrease forever without bound, and it never changes direction again. So looks like towards as x approaches +infinity, and as x approaches -infinity, those curves appear to be more linear. So I would say they're less curvy near that end behavior. Okay, so that's a very intuitive description. Let's talk about this idea of curvature. We want to be able to talk about these curves without using the term curvy, right? We're mathematicians. We like to have more exact vocabulary. Okay, so really this idea of curvature is related to the unit tangent vector that we've talked about a little bit this unit already. If you remember, that was that vector we called capital T of t. So a little bit of background information first, just some conditions we're going to need to have satisfied. A parameterization R of t is called a smooth parameterization if the derivative, the tangent vector, is continuous, meaning all of the components, the component functions of R have continuous derivatives. And we want that tangent vector to never be the zero vector. So none of the component functions can ever be simultaneously zero for a particular value of t. So if the parameterization is called smooth, then the curve, C, would also be considered smooth. Okay? Intuitively, this means that a smooth curve has no sharp corners or cusps. So when the tangent vector is turning, it does so continuously. Real basic example, something we've looked at quite a bit already, was our famous helix. The helix is an example of a smooth curve. Let's verify that. So we need to check that the derivative has continuous components. So let me do that. So r prime of t, this is our tangent vector, would be negative sine t cosine t 1. Okay. So clearly each of those components, I'm just going to put a little note off to the side here, continuous component functions. Okay, that's condition number 1. Condition number 2 is we can't have that vector be 0. Well, negative sine t cosine t and 1, first of all, the z component right away makes it clear that we're never going to get the 0 vector, but also even just looking at the first two components, sine and cosine are not going to be simultaneously 0 at the same time. Okay, there's nowhere where that would occur. So this is never equal to the 0 vector ever. So therefore, the helix is smooth. Okay? And that's what we really want to look at, is smooth space curves. Okay, just a little recap of the unit tangent vector. We're going to get into a little bit more detail with it today. So just to recall, the unit tangent vector, it is a unit vector, so it has a magnitude of 1. It's defined to be the tangent vector r prime of t divided by the magnitude of that tangent vector r prime of t. Okay? Dividing by that magnitude is what gives it a length of 1. Okay. We mentioned this the other day. Recall that capital T, this unit tangent vector, indicates the direction the curve is moving. So it indicates the direction of the curve. Okay. So this gives us a way to intuitively talk about the curvature, the curviness of that curve. Well, the curvature is defined in words, and we'll give a more mathematical definition on the next page, but the curvature is defined to be a measure of how quickly, should make you think derivative, how quickly the curve changes direction at a particular point. So really, if we, here's a space curve drawn in blue, we'll call that curve C, given by some parameterization r of t. The pink vectors are showing you the tangent vector, okay, or potentially the unit tangent vector if they have a length of 1. But notice in this area over here on the left, these tangent vectors don't look like they're changing direction too rapidly, but when we get into this little area over here in green that I'm circling, notice that they're changing direction much more rapidly. So we would expect the curvature there to be much larger than we would over here on the left-hand side. Okay. And then again, as we get over to this area on the right, where I'm kind of outlining in blue, again, the arrows don't look like those tangent vectors don't look like they're changing direction as much. It looks more linear in that area, so the tangent vectors look like they're generally moving in about the same direction. So just some observations maybe to worth noting here. Number 1, the unit tangent vector changes direction very slowly when C is fairly straight or fairly linear looking. So that would be like the left-hand side and the right-hand side. Capital T of t changes direction more quickly or more rapidly when the curve C bends or twists. Again, we're having a more intuitive description right now, but bends or twists more sharply. So really those areas where you can kind of see those on the graph right here, right? When I'm outlining kind of right over here in this area in red, it looks like it bends rapidly. Then it bends rapidly again right here where I'm putting a dot. Then it looks like it bends rapidly again up here. So there's definitely areas you can identify that are bending or twisting more sharply than others. Okay, so mathematically, we said it's a rate of change. It's a rate of change of how quickly the curve is changing direction. So that makes us think derivative. So the curvature, we want it to be a numerical real valued number. So we need it to be a magnitude of the rate of change of the unit tangent vector with respect to arc length. Okay, so mathematically, the curvature is the magnitude of the rate of change of the unit tangent vector with respect to arc length. In symbols, that would be magnitude dt ds. Why arc length? Because it's independent of the parameterization. We saw that in the first part of this section, that arc length does not depend on the parameterization chosen. So typically as a definition, we would like to define this derivative to be the rate of change of the unit tangent vector with respect to arc length, magnitude. The letter that we use for curvature is the Greek letter kappa. Looks like a little curvy K. Okay, so if you see that, that's talking about the curvature. Okay. Because the unit tangent vector has a constant length, right? Only changes in the direction are going to contribute to the rate of change of t. So we're not over quantifying this derivative because this unit tangent vector t has a length of 1. So only changes in the direction are contributing to this curvature. Well, that makes it clear. We can use that definition to think about the curvature of a straight line. If I have a straight line, the unit tangent vector just continues to move in the same direction forever. If you look at my sketch up in the top left corner right here. So it's not changing direction at all. So that would make it clear that for a straight line, our curvature should be 0. Okay? Because the unit tangent vector is constant. Okay? Now, it's defined to be the rate of change of the unit tangent vector with respect to arc length. Now, typically your parameterizations are given in terms of the parameter t. They're not given in terms of the arc length s. We saw in the last video how you can reparameterize with respect to arc length, but that can take some time to do. So there's got to be a way to calculate this curvature while still keeping your original parameterization t. So we can do a little bit of work to figure that out. If I wanted to define this in terms of t instead of s, we can use a little bit of the chain rule here. dt dt, I can write this as dt ds times ds dt. We can see that that differential with respect to arc length would end up canceling out. So this is a legal mathematical thing to write. And then if I want to be able to come up with an expression for dt ds, which I have inside those magnitude bars, all I would need to do is divide over this ds dt term to the other side. So I can define this curvature to be dt d little t over, I'm going to make my bars bigger, ds d little t. So it's the quotient of those two derivatives. And then recall, this little ds dt from our last section, that's just the magnitude of r prime of t. That was how we defined, we took the derivative of that accumulation function, that arc length function, and we ended up getting the magnitude of the tangent vector. So put it all together, this is just a quotient of two magnitudes. This would be the rate of change of capital T with respect to t, otherwise known as capital T prime of t if we use prime notation, divided by ds dt, aka magnitude of ds dt, which would be the magnitude of r prime of t. So notice now we've eliminated arc length from the formula. So we have a way of computing the curvature just from knowing the parameter t. Okay. I will say there's an easier version we'll see in a little bit. This isn't too bad to compute, but it might take a little while because trying to compute t prime takes some time. So for now, this is really the only thing we have. So let's use this to show, we're going to verify that the curvature of a circle with radius a is always the reciprocal of the radius. So that's kind of an interesting fact. Okay, if the radius of the circle is a, the curvature of that circle at any point will always be 1 over a, the reciprocal of the radius. So we need to define a circle. So let's let our plane curve, r of t, be given by a cosine ti plus a sine of tj. That's our typical parameterization for a circle with a radius of a. Okay. And we would assume that this circle, just the range of values of t, if we wanted to traverse this circle once, goes from 0 to 2 pi. Okay. Okay, so what do we need? We're going to need to define this capital T prime vector. So that means we're going to need the tangent vector, r prime. So r prime would be, I think I'm going to work in components from now on. So this would be negative a sine of t, a cosine of t. Okay. And so the magnitude of r prime would be the sums of squares of those components. So we'd have negative a sine t squared plus a cosine t squared. And so we would end up with a squared times quantity sine squared t plus cosine squared t. We can factor out the a squared. Our favorite Pythagorean identity, that's equal to 1. So I just have the square root of a squared which is A. Okay, so the magnitude of that tangent vector would be A. Okay, so keep going here. Now we can define capital T. Our unit tangent vector is going to be the tangent vector divided by its magnitude. And so our magnitude was A, so this would be 1 over A times the tangent vector. And so notice the A's end up canceling out. So we just end up with negative sine T cosine T. Okay. Okay, so now what do we need? Let's look back up at our curvature formula. We need the derivative of that unit tangent vector because we need to take the magnitude of the derivative. Okay, so this implies that T prime of T, if we take the derivative of this result that we just found, the derivative of that unit tangent vector would be negative cosine of T, negative sine of T. We need the magnitude. As I said, there's a lot of steps. The magnitude of that derivative of the unit tangent vector would be the sums of squares of those components. Okay. And as we've seen before, that gives us cosine squared T plus sine squared T, which is 1. Okay, so therefore, the magnitude of T prime is 1. And putting it all together, our curvature, if we take a look back up top, it's the magnitude of T prime divided by the magnitude of R prime. The magnitude of R prime was A. The magnitude of T prime was 1. So therefore, the curvature at T is going to be the magnitude of T prime divided by the magnitude of R prime. So we get 1 over A. And that's what they asked us to show. Okay. So takeaways. Let's think about this. If I have a small circle, has a small radius, that means it's going to have a large curvature. There's this reciprocal relationship between the radius of the circle and the curvature. Well, that would make sense if we think about it as the unit tangent vector changing direction, the rate of change of that unit tangent vector. It's definitely going to be changing direction more quickly because the circle has a smaller circumference. So those arrows are going to be changing more rapidly. Whereas if I draw a bigger circle, it has a larger circumference, so it has more ground to cover. Those arrows, yes, they're going to change direction, but they're not going to change direction so rapidly, right? Okay. They're clearly still completing the full 360 degrees, but they're doing it in a lot more time. So large circles, because of the big radius, if I take the reciprocal of a large number, I'm going to get a small number. Well, there we go. That means that we're going to have a smaller curvature. Okay. So think of it as the smaller one has to turn more quickly. Turns more quickly, whereas the small or the large circle turns more slowly. Okay, so here's 3 different curves. I want you to arrange those in order from smallest curvature to largest curvature. Pause me before you listen to me go through this one and give it a shot on your own, and then we'll check it. Okay, so let's check it. The first thing we have here is a circle that has a radius of 5, which means its curvature should be 1 over 5. The second, it's not even a curve, it's a line. The second thing we're given is a straight line. We saw at the start here that that means the curvature of any line would be 0. And the third thing we have is a circle, centered at 2, -3. That doesn't really matter. What I care about is the 1/9. That tells me that the radius would be the square root of 1/9. So it'd be 1/3. That means the curvature would be the reciprocal of 1/3, which is 3. So putting these in order, first curve has a curvature of 1/5. Our line has 0 curvature, and our third circle has a curvature of 3. Putting them in order from smallest to biggest, the line would come first, since it has 0 curvature. Then our circle with a radius of 5 would come next, so x squared plus y squared equals 25. And then finally, the circle with the smallest radius would come last. It's going to have the biggest curvature, x minus 2 squared plus y plus 3 squared equals 1/9. Okay. And again, just putting the curvatures underneath. This one had curvature 0. This one had curvature 1/5, and this one had curvature 3. Reciprocal relationship between the radius and the curvature when you're dealing with a circle. I mentioned a more convenient formula to calculate curvature. This, if you want to see the proof of this, the proof is in your ebook. I'm not going to do it on the video because I want to run through an example, which is going to take some time. But if you're interested in where this comes from, you can take a look at your ebook. So this is the one I would say we're going to use more often. The curvature is defined to be the magnitude of the cross product of r prime and r double prime divided by the magnitude of r prime cubed. Make sure that you remember that exponent of 3. Okay, so this is a way to basically calculate the curvature without having to directly compute the unit tangent vector and without having to directly compute the derivative of the unit tangent vector. So everything we're doing, we're just really doing from the original parameterization r. So I'm just going to say relies on r without directly having to involve the unit tangent vector. It's basically, the unit tangent vector is absorbed into this calculation. This is just a way of expressing it without actually seeing capital T show up. So this would be a good formula to put on a note card and make sure that you're studying. And we can see a cross product is involved. So let's look at one example. I'm only going to do one because these take some time to do. I would say as a good exercise, though, we're going to be computing the curvature of this twisted cubic curve. And I have this sketched on CalcPlot 3D. So we'll take a look at this once we're done with the problem. So it's given by r of t equals 2t, t squared, negative 1/3 t cubed. So the power of the polynomial is increasing with every component. And the first thing they want us to do is find the curvature function kappa of t. Okay. Now, there's two ways you could do this. You could use the formula for curvature that involves the derivative of the unit tangent vector. So we have two formulas now, right? We've got k of t equals magnitude of t prime divided by magnitude of r prime versus the one we just saw up top here, k of t equals the magnitude of r prime crossed, I think my camera's going to move out of the way here, r double prime divided by magnitude of r prime cubed. That might look more complicated, but I will say it's actually going to create less algebra for us to have to do. So as a good exercise for later, the one I'm going to do now is this one. I think you'll see that often has benefit. I would say as an exercise on your own, try it with the original definition that we came up with, which was t prime, magnitude of t prime divided by magnitude of r prime. You're going to get some good algebra practice there with some factoring and with using some quotient rule. But you'll get the same result. And this version I do have on my key that I posted on Google Classroom. I have both of them, but if you want to try it on your own, I would try the original definition that we did first. And then we're going to do this one on the video with the new formula that I just gave you that relies only on r prime and r double prime. Okay. All right, so let's kind of do this step by step. What are some of the tools we're going to need? Well, we're going to need the tangent vector r prime, and we're also going to need the second derivative because we're going to need to take the cross product. So let's do this step by step and not rush it. Okay, here we go. R prime, taking the derivative of the position function here that they gave me, the space curve, we get 2, we get 2t, and we get negative 3/3 would be negative 1, so negative t squared, just using a little bit of power rule 3 times. And then the second derivative, the derivative of 2 would be 0, the derivative of 2t would be 2, and the derivative of negative t squared would be negative 2t. Okay, I need a cross product. So r prime crossed r double prime would be ijk. Putting my components of r prime in the second row, I get 2t, negative t squared. Putting my components of r double prime in the third row, I get 0, 2, negative 2t. And so let's see what we get. Okay. We end up with I times, crossing off first row, first column, I'm going to have 2t times negative 2t would be negative 4t squared, minus 2 times negative t squared would be plus 2t squared, minus j, remember to flip the sign, Crossing off first row, second column, I would have 2 times negative 2t would be negative 4t, minus 0 times negative t squared would be minus 0, plus k, times, crossing off first row, third column, 2 times 2 would be 4, minus 2t times 0 would be 0. So we end up with negative 2t squared, positive 4t, once I distribute the negative sign, and 4. Okay, we need the magnitude of that cross product. I'm running out of space here. Let's see where I want to go. I'll keep going. So magnitude of r prime crossed r double prime. I'm going to keep my t's just to be consistent here. So r prime of t, it's kind of implied that it's a function of t, but. All right, so taking the sums of squares of the components here, what do we get? We're squaring and summing this component, and this component that I'm highlighting. Negative 2t squared would be 4t to the fourth. 4t all squared would be 16t squared, and 4 squared would be 16. Okay. I'm going to clean that up a little bit. You'll see why for when we get to part B, because we're going to end up having to take the derivative of something that involves that expression, and that would be kind of nasty. So let's factor a little bit. We can factor out a 4 from this. And so I get 4 times t to the fourth plus 4t squared plus 4. This 4 can come out as a 2. So you get 2. And this expression is a perfect square, binomial. So that factors into t squared plus 2 quantity squared. Square root of t squared plus 2 quantity squared would be 2 times t squared plus 2. No absolute value bars needed because that expression is always positive. Okay, so that's the numerator. That's our numerator of our expression. So I'm going to come over here because I'm running out of space. So the curvature, if we look and move my video out of the way here, the numerator is going to be that cross product, magnitude of that cross product we just found. 2 times t squared plus 2, divided by the magnitude of r prime cubed. Well, we have the magnitude of r prime here. If we divide by the magnitude of r prime, I don't think we've computed that yet, so let's do that. Where do I have space? I have space over here. I'm going to draw an arrow. You might have written a little smaller than me and have more room. So the magnitude of r prime of t is going to be the square root of 2 squared would be 4, 2t squared would be 4t squared, and negative t squared all squared would be t to the fourth. That's another perfect square binomial. That's actually the same one we just did. T squared plus 2 quantity squared would be t squared plus 2. So the magnitude of r prime is t squared plus 2. And don't forget, look at your exponent. We have to cube that. So we have a power of 1 on top and a power of 3 on the bottom with the same base, the base being t squared plus 2. So subtracting those exponents, 1 minus 3 would be negative 2. So my curvature ends up being 2, and I'm going to move the negative exponent to the denominator, divided by quantity t squared plus 2 squared. Okay, so that's my curvature function. And then I can evaluate it. The idea is that at different values of the parameter t, I can figure out the value of the curvature along the curve for different values of t. And we want to try now in part B, the whole point of this, is to figure out where is the maximum curvature. And you can take a look on Calcplot 3D. I have some instructions actually for how to generate this twisted cubic. So if you want to try to generate this yourself, I don't know why it's not. There we go. And I posted these on Google Classroom also, but if you go to Calcplot 3D website, you're going to add a space curve to your graph menu, enter in the component functions that we have in the example for x, y, and z, set your parameter values to go from -10 to 10, change the number of steps. I think the default it has is 500, change it to 1,000. It'll ask you for how many orientation arrows you want, change it to 10. Hit the little checkbox that shows up next to the trace, and then animate it, and you can watch those tangent vectors move along the twisted cubic curve. And I think if we remember, there's different colors of graph. Let's see for a second. So if we animate this, yeah, you're going to want to look at the blue vector. There's going to be a blue vector, a black vector, and a green vector. The blue vector is going to be the one that indicates the direction of the curve. That's going to be your tangent vector. Oh, I'm sorry. No. Sorry. The black vector is the one you want to focus on. The blue vector is just the original position vector that points out of the origin and hits the space curve. The tangent vector, which they're calling v, you can predict that's probably for velocity. We're going to talk about the PVA context of this in the next section. Look at the black vector. That's going to be indicating the direction of the curve. That's showing you the tangent vector. So you want to animate this and just kind of watch. Think about where is it changing direction most rapidly, at what point on the space curve. Can't see it yet because it's still animating, but it's that blue vector is tracing out just the position, and the black vectors should start popping up here. There we go. So you can see that's showing you, it doesn't look like it's changing direction too rapidly yet, but now the curve's getting closer together and it looks pretty rapid right around there. Looks like it's changing direction pretty quickly. So maybe your prediction is somewhere near the origin, or maybe not. Okay, spoiler alert, I did add the 0.000 to the graph, so there's probably a reason for that, but let's check. So at what point on the curve does maximum curvature occur? In other words, where is the tangent vector changing direction most rapidly? And furthermore, second part of the question, what is that maximum curvature? Okay. What is the value of the curvature? So we just found in part A, the curvature function was 2 over t squared plus 2 quantity squared. Okay. And now we want to maximize the curvature. Okay. So this turns into a Calc 1 problem now. How do we maximize a function of one variable? Well, we take the derivative and we find the critical points. So I'm going to take the derivative of my curvature function. It would help to actually write this as 2 times t squared plus 2 to the negative second so that I can use the power rule. 2 times negative 2 would be negative 4 times t squared plus 2, decrease the exponent by 1 to the negative third. And I am going to write this as negative 4 over t squared plus 2 cubed. Okay, critical points. We need to figure out where the derivative of that function is either 0 or undefined. So I'm going to set this equal to 0. Okay. Oh, I forgot my chain rule. Uh-oh. Let me do that again. Times, forgot, we got to multiply by the derivative of the chain. The derivative of t squared plus 2 would be 2t. Sorry about that. So we get negative 8t over t squared plus 2 cubed. There we go. Okay, setting that equal to 0. Values of the numerator equaling 0 will tell me places where the derivative is 0. Values where the denominator could equal 0 will tell me where the derivative is undefined. Notice that this quantity is always greater than 0, so your denominator will never be 0. So that tells me the derivative is defined everywhere. Values that make the numerator equal 0 would be t equals 0. Okay? So k prime of t equals 0 when t equals 0. So that's my critical point. So CP is critical points. And then you probably made sign charts last year in Calc 1. So if I make a sign chart here, I'm going to put my derivative in the top row, and I'm going to put my original curvature function in the bottom row. I'm going to put my critical point on the chart, t equals 0. At that point, the curvature, the derivative of the curvature was 0. And then I'm going to plug in expressions or values of t into my expression negative 8t over t squared plus 2 cubed. That was my derivative of the curvature function. And if I plug in a value of t to the left of t equals 0, let's just say we plug in t equals negative 1, then I'm going to get negative 8 times negative 1, which is a positive, divided by, we said the denominator is always positive. A positive divided by a positive is a positive. So the curvature function is increasing from negative infinity to 0. Let's test a value of t to the right of 0. Let's test t equals positive 1. Negative 8 times positive 1 would be a negative value, divided by a positive denominator would give us a negative result. So from 0 to infinity, the derivative of the curvature is negative, which means the curvature itself is decreasing. because the curvature is changing from, the derivative of the curvature is changing from positive to negative, or you could think of it as the curvature is changing from increasing to decreasing, that tells me that we have a local maximum at t equals 0. So that value of t equals 0, maximizes the curvature. So now let's answer the question. At what point on the curve does maximum curvature occur? Well, we just said it's when t equals 0. So r of 0, we go back up to the original function, would give me 0, 0, 0 when I plug in t. That's a vector. They asked for the point, so I'm just going to clarify here. That tells me that maximum curvature occurs at the origin. And on the graph that we showed on CalClot 3D, it looked like that, so we'll animate it one more time at the end here. They also asked what is the value of the curvature. So the curvature, I'm going to call it K max, is going to be plugging in 0 here for, sorry, we have to go back up to the original function. There we go. This was our curvature function, 2 over t squared plus 2 squared. So we're calculating k of 0. So we end up with 2 over 0 squared plus 2 squared. So we get 2/4 or 1/2. So that right there, that's our maximum curvature. So that's where it's changing most rapidly, is at 0, 0, 0. And the value, the magnitude of that rate of change of the unit tangent vector with respect to arc length, that definition, that curvature, has a value of 0.5 or 1/2. So let's animate that one more time just to take a look. Okay. Yeah, so if we animate this one more time. Okay, so you don't see the tip of the blue tail. Maybe if I zoom out a little bit, we could see it. There we go. Yeah, I got to zoom out quite a bit, but we can at least... It's eventually going to reach there. Right now we're at about t equals -5. We're going to t equals 10. So look for the black vector. That's your tangent vector. Okay, it doesn't look like it's changing direction too rapidly yet. It's just moving along the curve. Now it's bending and twisting more sharply. And the origin, oh, I probably should make the origin pop up. Let me do that. There's 0, 0. Can we see it? I don't know why the point's not. There it is. Let's try it one more time. Let's animate this. Okay, so you focus on that pink point, that origin. That's going to be where the maximum curvature occurs. That's when it's going to change direction most rapidly. Okay, so it's moving, it's moving. I'll take a sip of my coffee in the meantime. Okay, focus on the black vector. That's our derivative vector. That's our unit tangent vector. It's our tangent vector. And look at how it changes direction fairly rapidly right there at the pink point. Okay, that's the origin. That's where the maximum curvature occurred. At that pink dot, that was the curvature of 1/2. Okay. So again, the directions for animating this on your own are right here if you want to pause the video and take a look at that and try this out. The more you can use CalClot 3D to actually animate some of these examples, I think the easier time intuitively understanding what's going on you'll have. So a lot in this section. This is a pretty formula heavy chapter. So again, I would make some note cards for the various formulas we're going to do, this being one of them. And I would also add this one to your list also. These are 2 different formulas we can use to compute the curvature. I would say those are 2 of the biggest takeaways from this section. The other biggest takeaway is that for a circle, where did we have it? For a circle, the curvature is the reciprocal of the radius. That was another big takeaway. So any circle I give you now on a quiz or test, that'd be a good question. I could give you a circle and ask you to give me the curvature. Just realize that small circles have large curvature and large circles have small curvature. It's a reciprocal relationship. So that's one of the biggest takeaways from this video. All right, so there is still more to this section. What about, how do we find the curvature of just a plane curve? If I give you a function f of x and I ask you to figure out the curvature at various points, there's got to be a way to do that when we're not given a parameterization. So we're going to take a look at that. And then in the next section, we're going to get into the concepts of position, velocity, and acceleration, and we'll be able to talk about some of these components also. Okay? Hopefully that is helpful. You can get started on some homework for curvature. See you in the next video.